Thank you very much. Thank you for the invitation. Very nice to be here. Very nice to see everyone. Okay, so this is some work with Mark Holland. And I think it turns out that I'll be introducing some kind of general extreme value theory and dynamical systems topics through this. So maybe this is kind of, turns out to be quite a good option for a first talk. Okay, so the first section is on first hits. So I'm assuming that F going from I to I is a dynamical system, and I'm thinking about I as being the unit interval. Of course, a lot of this stuff generalizes. And mu an F invariant probability measure. And pretty much through this talk, it's going to be absolutely continuous with respect to Lebesgue. So, absolutely. Oops. Continuous with respect to Lebesgue, i.e. ACIP. Okay, so standard setting in this area now is to take a point in I and take some G, some observable, so this is just some function, going from positive reals into the extended reals, and a function taking a maximum at 0. Okay, and the standard cases we're going to see here, our cases are g of x is equal to minus log x. I'll mostly start with that one, and I'll mostly end up with g of x is equal to minus x. Okay, so given that, I'm going to set xn of x to be equal to g of the distance of fn of x to z. Okay, so we're seeing, are we close to z? If we are, then xn of x is very large. Just say that, so xn large, x close to z. Okay, so we're interested in extremes. These are our rare events. And so we set, so often this is called M, but I'm going to follow Collet and call it Z here. So this is the supremum. And, well, it sort of depends where you want to start, but I'm going to start at 1. Supremum of the XJs, and maximum. Doesn't matter. Okay, so I'm interested in how this function behaves. And as I guess many people in the audience know, the kind of founding result in this area, in many ways, is a paper of Collet in 2001. And so his result was that if F has a young tower, I won't go into, with exponential tails. So some nice setting for mu almost every z. Right, so z is the point we want to be close to. Right, so I pick my z. How close am I to z? Mu almost every z in I. And here I'm assuming that mu, as I said I would, is an ACIP, and here g is equal to minus log. Then Collet proved that the limit as n tends to infinity of the measure of this maximum thing being less than v, some parameter that you just can pick, plus log n, well, this tends to e to the minus 2 rho z e to the minus v. Okay, so what's rho? I said this was an ACIP, so d mu is equal to rho d Lebesgue is the density. Okay, so the idea there is that this converges to the same law as the corresponding IID process, as the corresponding IID process with distribution mu. Okay, fine. Yeah, and then note, because it's going to be useful later, that if g of x is equal to minus x instead of log x, so we get the same thing, except so v plus log n goes to v over n, and e to the minus v goes to v, I think. Okay, fine. So that's the sort of now considered classical in this area result. Now, another thing you did in this paper, which people haven't followed up so much, so lots of people have followed this stuff up, is a more difficult situation. Which is self-recurrence. So here, instead, xn of x is equal to g of the distance from f to the n of x to x. Okay, so you're seeing how close, so you take your x, you see how close the iterates of x gets back to x again. Okay, so you no longer have this fixed z, it's a different setting. So, e.g. more difficult, so if you look at the distribution function, it's not going to be the same at every step. If you take n and n prime, and you look at the probability of this being greater than t, it's not the same as this as xn prime being greater than t, which it was here. And that kind of, so this kind of thing is going to cause problems when trying to compare it to a corresponding IID process, maybe. Yeah, so it's somehow further from IID. Right, so in the Collet case, try to show that asymptotically the maximum behaves like the maximum of the IID process. And here you might think, well, maybe this is going to be more difficult. Well, it is a bit more difficult, but Collet showed that he could actually get the same result, essentially. So nevertheless, theorem 4.1 in that paper says, so same setting as theorem 1.1. So the limit as n tends to infinity of mu zn less than v plus log n, so the same normalizing constants, is equal to, well, so previously we had e to the minus 2 e to the minus v rho, but it's not that, it's an integral of that, rho x. Nope. So this is the maximum. So I haven't, yeah, okay, this is, I should have mentioned that. So here's z, so Zn is the supremum of all of those. But now I've changed my x's to these ones. But yes, I should have mentioned that, thank you. Any other questions or comments on this? So in extreme value theory, there are three types. There's the viable, there's a Frechet, and there's the Gumbel. So you expect, you have to look at three different types. These are two of those types. A lot of the first papers were interested in this Gumbel one. In this talk, I'm going to be more interested in this one here, the GLX is minus X. Any other questions? Okay, so the proof uses a decorrelation argument. So the idea is you want to go from looking at G of D of Fnx x to G of D of Fnx z for some kind of z by splitting the interval into small pieces. So I'm going to come back to this idea again later, but I'm going to quickly mention it now. So you take your interval 0, 1, and you carve it up into, these are supposed to be very tiny, and what you do then is you then fix your small interval and consider hits to a neighborhood of this. So this small interval here is like your z. Okay, so as you shrink it, it becomes more and more like a point. This is like your z. And then you use hitting from theorem 1.1. Okay, so as I say, I'll come back to that sort of argument again later. And let me just note, before I move on, that Penn and so Sol in 2010 proved a similar result. For some Asa billiard maps. Right, so the idea of you have to integrate over something like this rather than getting something fixed like that. Okay, so those of us who worked in this kind of stuff, okay, well you're interested in, that's the first hit, the first time you get close to Z, or the first time you get Fnx gets close to itself. Well, how about, yeah, go on. In this sketchy argument here, yes, it's sort of, it turns out only the generic ones matter for this part of the argument. Yeah, so that's another thing I could highlight at this point, thank you. That this is for generic points, but as we've seen, if you take, for example, Z a periodic point, then you would get something else in here, you get some extremal index parameter in there, but that's not typical. And it turns out that these results only really see the typical stuff. But yeah, you have to show that that's true. Yeah, so the next question then is, how about counting hits? Okay, so as I say, given an exponential law for first hits, next natural question is about Poisson type laws or numbers of hits. Okay, so I could introduce this through the hitting to as a particular Z, but I'm going to actually focus from now on in the talk to this self-recurrence type problem. Okay? The questions about hitting some Z have been looked at by including me and lots of people in the audience. Okay, so the problem is we set Rn, Rx to be the count of how many j in between 1 and n such that the distance of x, fj of x, is less than r. Okay, and we're going to choose specific choices of good choices of r. So that's what I'll say next. So I want to find good Rn such that the measure of the set of points such that Rn, little rn of x is equal to k for some given k tends to something. Okay, so that's the plan. So the candidates you can for the Rn's are these scaling sequences. So if I had minus log, then something like v plus log n. But here I'm going to look at g of x equal minus x, and so the natural candidate then is something like v over n. Okay, so my Rn is some multiple of 1 over n. Think of g here as g of x is equal to minus x. So natural candidate for Rn is, well, it'd be v over n, or c over n for some c. I'll be more specific later. Okay, so what I'm going to do is I'm going to give the assumptions for our result, explain what our result is, and then try and give you some idea about how that works. So here are the assumptions. So the first one is I, f, mu has exponential decay of correlations for BV against L1. Oh, and I'm assuming, mu and yeah, fine. Okay, so this is a standard type of assumption. It's relatively strong, I suppose, but it's a standard one in this area. And the second one is something that appears more explicitly in Collet's paper. If I want some sequence Sn, which is polynomial decaying, so if I have something like that, there exists a beta, say, some fixed a greater than 0, there exists a beta and c greater than 0 such that if j is less than or equal to log n squared, then mu x such that d x j of x is less than or equal to Sn is less than or equal to c Sn beta. Okay, so this is the first one is like a mixing condition, and the second one is like a short recurrence doesn't behave too badly. So you don't have too many points coming back too fast. So if I take A1 plus A2, We call this hyperbolic recurrent. Convenient to give these things a name. But someone wants to tell me it's a bad name, that's fine. So here's the theorem. And now I'm going to use my own numbering system. So this is with Mark Holland. So if our system is hyperbolic recurrent, then for Rn is equal to tau over 2n. 2 is just to get rid of this thing here. For all k greater or equal to 1, limit as n tends to infinity of the measure of the set of points such that Rn, little rn x is equal to k is equal to, well, previously we had this integrating over the exponential law, and here we have integrating over some kind of Poisson thing. Tau to the k rho of x, k plus 1 over k factorial, e to the minus rho of x, tau dx. Okay, so it's a sort of averaged Poisson. And just to say quickly, so note, if rho of x, the density is identical to 1, so e.g. for f, doubling that, and mu is equal to beg, the limit is just what you'd expect from Poisson. Okay. K factorial. Okay, so that's the result. The next thing I'm going to do is try and give you some idea about how the proof goes before talking about some further results. But does anyone have any questions before I do that? Okay. I'm going to delay the cleaning of the boards, which is always a scary thing if you haven't done it for a while in a Germanic setting. Okay, so the proof, again, uses splitting of the space. Into pieces. So now I'm going to be a bit more detailed about that. So pieces delta of size, we call these 1 over 2m. M is going to be some integer. And considering the hits to neighborhoods of these of order size tau over 2n, and the idea is that m is much, much bigger than n. And in fact, what we usually use is m is equal to n to the 1 plus beta prime for some beta prime. Okay, so these pieces we cut it into are going to be much, much smaller than the neighborhoods we're worried about. Okay, so let me just sketch that very basically. So here's my interval 0, 1, and then here's my delta. And then, oh no, that's not my 0. Sorry. My piece is going to be delta, and then I'm going to look at a neighborhood. So it's going to be a size 1 over 2m, and then this size here is going to be 1 over 2n, And this thing here is going to be called delta 0. Okay, so, and I think about the interval is going to be some massive thing here, and they're going to cut these into these little pieces and look at neighborhoods of these little pieces. Okay, and then the idea is to look at nn of delta 0 x, which is going to be defined as the number of j's between 1 and n, such that f to the j is in delta 0. Okay, so notice I've done my decorrelation. Well, I've started my decorrelation argument here because now I'm looking at hits of x to some fixed interval rather than hits of x to some neighborhood of itself. That's the key point here. Okay, so I'm going to give you some propositions which are going to kind of outline the proof, but I'm not going to go into the proof very much. So the first proposition is that if I look at the quantities that I'm actually interested in, i.e. the Rn quantity, I can estimate this in terms of the Nn quantity. So I take delta, I intersect it with Nn delta 0 x. Okay, we'll move out of the way in a minute. And then I sum that over all the deltas, and this is going to be less than or equal to some error term, which we compute, but this tends to 0. Okay, and the proof of that part is relatively straightforward. Yes, thanks, Todd. Please bear with me. Usually I try and talk about my talk as I'm cleaning the boards, but my concentration is so intense on doing this properly that I can't do that. Okay. Right. So yeah, the proof of that is relatively straightforward. So I won't really talk about that. So the next step here is the crucial use of the Chen-Stein method. Okay, so next step. Okay, so for random variables, U and V, total variation between these is equal to a half times the sum k equals 0 to infinity of probability U equals k minus the probability V is equal to k. Okay, so Chen-Stein, I'm going to use the version from Chazot and Collet in in 2013. I say version, they had to do some work. This is not immediate, but they have a nice version there. So the proposition is that the total variation between NN delta 0 Poisson with intensity n mu delta 0. You can see why you want these things this one to be the inverse of that, right, more or less. Brackets. This is less than or equal to some error term, which I am not going to talk about. But working out how to deal with this error term is one of the key parts of our paper. Okay, so together, these propositions, I get proposition 3, which is that the measure of Rn, little rn x, is equal to k minus the sum over all these deltas, mu delta, n mu delta 0 to the k over k factorial e to the minus n mu delta 0. Sorry, that's a bit small. The distance between these two things is again less than or equal to some error term, which again is crucial for us to calculate, but I'm not going to talk about that here. Okay, so hopefully you can then see it as believable that this kind of sum is going to converge to, thank you, this type of integral, right? Use the dominator convergence theorem, it works. So that's the track. Okay, so the main work here is showing our estimates for, well, all of these thetas converge. Okay, so that's basically how the proof goes. So that's the first theorem I want to talk about with a sketch of the proof. The next thing I'm going to do is talk about some almost sure results. Does anyone have any questions before I do that? Some time to read my poor handwriting. Okay, so we also have some almost sure results. And these, just say this type of result in theorem 2, we're not aware of anyone, theorem 1, sorry, we're not aware of anyone who's done anything of this type since Collet. Well, and that pentasol result. For this case, there is some recent work which is comparable. I will compare. So we can also ask questions of the form for which sequences Rn is mu x such that d fn x less than Rn infinitely often equals 0 or 1 or whatever, infinitely often. Okay, so that's a question. So these problems, I think many of us will say that these go back to Poisson. At least the way we think about them now. So me say that as in a recent work of Holland, Kersabom, Kunde, Poisson. Okay, so I'm going to call those HKKP. The above quantity here, a trick to say that the above is the same as the set of points such that the minimum J less than or equal to N D F to the J X is less than Rn infinitely often. Okay, so I want to put it into a sort of extremes context and put it into minimum here, puts us on that road. So actually what we're going to do is we're going to talk about the opposite set, the set where you're bigger than that eventually. The ideas are very related. I'm going to say something next so you can complain about that. Yeah. I'm sure there'll be other things to complain about, don't worry. Okay, so theorem C of AKP 23. So there's two papers. There's HKKP and there's there's actually more than that. Anyway, so one of them says that this is 0 if the sum, the integral, the measure of the Rn ball mu is finite. So we ask about the complementary setting. Okay, so what's that? So the theorem 2 self and Mark is that in the same setting as above, as in theorem 1, firstly, if the density is bounded away from 0 and Rn is greater than C log n over n, for 2C min rho greater than 1, then the measure of set of points x such that the minimum k equal to n dfnx a x x less than Rn eventually is equal to 1. Okay, so well, let me write the results and then I can try and comment on them. The second one is something we put here for context. Really, it's not really our result. really, but useful for comparison. Followed by the previous result I mentioned, then the measure of x such that the minimum greater than n. So if it's greater than n now, eventually 1. So, well, you can imagine here that you can imagine like you want balls that are just a little bit smaller than 1 over n. And here I've got something quite a bit bigger than 1 over n. So, there's still some gap in here, but this is an improvement on the state of the art. So B follows from E. For A, KKP theorem E required Rn greater than 1 over n to the gamma for some gamma greater than 1. I should also say they also look at a broader range of systems. Oh, sorry. Yes. Thank you. Yeah, they also look at non-ACIPs and Rn. Also, Rn can depend on X. Okay, so there's other things that they do there, but you can see that the Rn here is better in this setting. Okay, so let me just give you some idea about how that proof goes very quickly. But before I do that, does anyone comment on that? Okay, so the proof, it's linked to the previous stuff, but not super intensely. Because really all we're interested in is estimates on mu of Rn is equal to 0 rather than k. And the crucial estimate crucial estimate is for some alpha 2. I'm calling it alpha 2, anyway. That's what we call it in the paper. Mu Rn x is equal to 0. We get that this is less than or equal to C n to the minus alpha 2 plus C1 e to the minus 2C log n. Okay, so this is what this term here is what you see in the recurrence thing here when you put k is equal to 0, but then you're interested in the error term, and the error term is this error term here, and that's what allows everything to go through. Well, okay, you'll notice that this is for some alpha 2 greater than 0, which may not give something summable. So we're thinking Merrill-Cantelli here. This is not summable, but you can use a trick of going along exponential subsequences. Okay. A greater than 1. Okay, so that's my almost sure result. Or at least the first one. And I don't really need all this blackboard, but I'll clean it anyway. I'm going to finish by talking about systems which don't satisfy A1 and A2. As I said, are fairly stringent. And well, as you might guess, the this is big. The proof goes, extending that goes through inducing. So inducing in some specific settings. We can handle some more things than just those where you have decay of BV against L1. Using, so theorem 3, last theorem, if we can puncture the system put a hole in it so that the induced system first return, so induced, so first return system, I should say. It's important that it's first return. Is hyperbolic recurrent. Then the conclusions of main theorems hold. Well, I'm assuming I'm starting with an AKIP. So, yeah, that's hidden assumption. So, for example, our old friend Poisson, and also you can look at some Misiorowicz-Thurston maps, well, all of them. So for those ones, if you can remove a part of the system and you still, when you take a first return map, you get something which has nice properties, namely A1 and A2 hold for that. So those are some more examples, and I will stop there. Thank you for your attention.